Hi, in this example, we are going to see how to design decoders. The decoder design is actually very easy because, as we know from the decoder operation, the decoder implements all the minterms of uh, of the input variables at its output ports. Okay, so D0 will be minterm 0, D1 will be minterm 1, and I just need a few gates to implement any of those minterms. So basically, if in a regular active high decoder D0 is equal to minterm 0 of the input variables, it means it will be A1 complemented, A0 complemented, and it can be done just using an AND gate and complementing the variables with an inverter. The same is true for the rest of the outputs. So to draw a circuit that allows to generate all the minterms, the easiest way is to draw it like this. We have A1 here. We'll draw a line. We'll draw a line here for A1. We'll draw another line here for the complement of A1. Now we'll have A0 here, its complement here. And now we can start drawing it. We'll use an inverter to generate A0, to generate A1 complemented. A0 is here. We will use an inverter to generate A0 complemented. And now we just need gates to generate each minterm. Okay, I'll have D0 here, D1 here, D2 here, and D3. So D0 is A1, A0 complemented, so we'll connect right at these points here and here. For D1, it is A1 complemented A0, so we take A1 complemented here, A0. This one, D2 is A1 and A0 complemented, and D3 is A1, A0. So the idea is that the four outputs are really very simple functions that are obtained like that. So a decoder is a nice device. It helps solving a lot of problems, but it's not a really complex device to implement. Now, what if we want to do a complex with active low outputs, okay, and we want to include an enable? In the slides, we had a version with active high enable. Here we want a version with an active low enable. So we operate in the same way. Actually, we can think of this problem in different ways. Let's see what happened, for example, with D0. D0 is the minterm the minterm 0 but complemented. So actually we have in D0 we'll have minterm 0 complemented. Okay, so we can think of it as A1 complemented, A0 complemented, and now it's all complemented. Okay, it could be done with a NAND gate. So we could simply use basically the same design we used in the previous decoder, but just use NAND gates. This is an option to implement that. The exercise says design the decoders using logic gates, so that will be a quite direct way to do it. Okay, but we need to use the enable. So the enable mean that we wanted to activate only when the enable is equal to 0. Okay, so we can add that signal. So instead of that, we will use something like this 0 will be the n minterm 0, but which is activated only when the enable is equal to 0. This is the difference with the example in these slides. Now it's minterm 0, A1 complemented, A0 complemented, and now everything is complemented. So when A0 is 0, then it's a 1, we have the minterm, and the minterm complemented is our output. Okay. We can also think about it like having a max term. So actually, the complement of a minterm is a max term, and the active low decoder is a decoder that generates all the max terms. So this 0 could be something like max term 0, which is equal to A1 or A0, the term that is 0 when A1 and A0 are 0, right? But we need to add the enable. So basically the enable does, we have our max term, but it will be 0 only when the enable is 0. Otherwise it will be 1. So we basically add the enable and adjust the complement. So in this case, we can see that when the enable is 0, we have the max term. So we will need to complement it, I think, like this. Okay, so now when the enable is it's like this. When the enable is 0, the device is enabled. So we can simplify this, and we have the max term. When the enable is 1, we have 1 plus anything. So when the enable is 1, this output will be 1, and 1 in this case means it's not active. Okay, actually this is the same result we achieved by thinking in the min terms. So no matter how you deduce the solution, it's quite the same. If we apply De Morgan here, we have the complement of E complement, which is E, A1, that's A0. Okay, we think about taking a min term, we enable or disable the min term, and then we calculate the complement. Or we can think about generating directly the max term and use E to enable or not, to force it to be a 1 or not. Okay, any way we reach the same conclusion. Okay, now how do we draw the circuit? One option will be, as I said before, start with the circuit we already had here. I'll make a copy of it. Let's try again. Okay, let's make a copy of that circuit. Great. Let's make it a bit smaller. Over here. So we could use a similar approach we have done before, and but simply what we have to do is to complement these gates. So we use NAND gates instead of plain AND gates. And now we add the enable. You see in the input of the NAND gate, I include the enable complemented. So we'll have the enabled signal here, we complement it, And now from this line, I add connections to all the gates here. Yes, more or less like this. Okay, so this is by thinking in terms of min terms. If we think in terms of max terms, then we can realize that it's simply OR gates. Okay, so we can do it in a very similar way. So I'll reuse part of the circuit. Let me copy it here. So now we will have, instead of E complemented, we'll have E directly here. I will add E to all the outputs. So in this case, instead of NAND gates, we will use, oh, I'm deleting more than I expected. We will use OR gates to generate my outputs. Great, and that's it. Now I have to change the connections, all these connections here, because now the first max term is the one that is 0 when A1 and A0 are 0. So we need to use A1, A0, and of course we use the enable here. Okay, this is 0 when we have a 0, 1. Okay, so here I take the variable and I take the complement of this whole variable, and of course we take the enable. Now this is 0 when we have a 1, 0, so we have to complement now A1. We take A0 and the enable. And now for the third output is 0 when both inputs are 1, so I use the complements. This complement, and also the enable. Okay, so all these will be the two options to implement that circuit. Okay, with NAND gates or with NOR gates, as there's also other options to implement this as the active high decoder. From what we know from previous lessons, in most cases, in most technologies, actually NAND gates are more simple than more efficient than OR gates. Okay, because actual gates in most modern technologies are naturally complementing gates. So we will rather prefer this design better than this design here. Okay, so it's good to have alternatives, because even if we think in our problem as a max term generator, in practice the other solution may be better, so we will prefer this one. Okay, but now another important conclusion of this example is that decoders, as it happened with combinational subsystems, are what we call modular designs. They are designs where all outputs can be derived from the actual meaning of these outputs. We don't need to think as a general combinational problem, so we don't need to use the Carnot maps and everything, okay, and treat it as a generic problem. We use what we know about the regularity of the device, and by applying that, we can reach to a solution in a more simple way. Okay, that's all. Thank you.